Ionization energy is how much energy it costs to take an electron off a gaseous atom. This is a gaseous mole of atoms here, so magnesium gas. When we form magnesium ion, which is Mg2+, we have to think of it as a two-step process. We pluck one electron at a time. And so the first electron that comes off will form magnesium with a +1 charge. It's going to cost you about 700 kilojoules. And then if we take magnesium plus and pluck the second electron, it's going to cost you an additional 1,500 kilojoules. And so altogether, it's going to cost you 2,200 kilojoules to form a magnesium 2+ ion. 2,200 kilojoules is a lot of energy. It's a lot of energy. And normally when we think about magnesium, we say magnesium is an excellent reducer. It's a good fuel. Magnesium burns. It burns with a bright white flame. And in fact, magnesium is used in flash bulbs, because old-fashioned flash bulbs, because of the bright white light it produces when it burns. And so why do we even bother forming magnesium 2+? You know, in order to form magnesium 2+, it costs us 2,200 kilojoules. Why not stop at 700? Why not just go magnesium plus? Because magnesium plus is going to cost a lot less energy, only 700 kilojoules. In fact, why even bother taking any electrons off magnesium? Just leave magnesium alone, and then you don't have to spend this. You know, if you're going to spend $700, you probably can, or 2,200. You know, would you do it? No, it doesn't make sense. So there's a disconnect here, because magnesium is a powerful reducer, and yet it costs a lot of energy to take the electrons off. And so why doesn't it stop at +1? It doesn't stop at +1 because if this were it, then nothing would happen. But it doesn't stop at +1 because it's much more beneficial to go to +2. Why +2? Because we don't see what happens afterwards. You can't just have a jar of magnesium cations. You have to have anions. When you have anions, you form a bond. When you form a bond, you release a lot of energy. Bonds are stable. And so the reason it goes to magnesium +2 is because we'll form a much stronger bond in the end. Well, you know what? If we went to magnesium 3+, you know, the higher the charge, the stronger the bond, because there's going to be a stronger, what we call Coulombic attraction. That is, the positive cation will be more strongly attracted to the negative anion. And so you're going to form a heck of a lot stronger bond with magnesium 3+. And actually, we should keep going, because at magnesium 4+, that will be an even stronger bond, right? But it stops at magnesium 2. Why does it stop at magnesium 2? It stops at magnesium 2 because of this. It's cost versus benefit. Yeah, sure, it's going to cost you 2,200 kilojoules, but you're going to get more kilojoules in return. And so your initial investment will be 2,200, but your return will be greater than that, so you'll make all your money back that you spent. But to make it a magnesium 3+, which will make an even stronger bond, is going to cost you a lot more, an additional 7,733 kilojoules per mole. And so it's going to stop here, because this is a core electron, and to ionize a core electron just costs way too much energy. If the bond were strong enough and you get a return, then you can ionize a core electron. People try to do this. They try to form magnesium 3+ compounds, trying to figure out how to bond this to stabilize that charge. And so sodium, you know, sodium is going to stop at +1 because, you know, the cost versus the benefit is good. But if you try to go to sodium +2, forget it. It costs too much energy. And so what we see here is the valence electrons are reasonable to ionize, but once we get to core, the core electrons are going to be significantly more energy to ionize. And so the common charges are sodium +1, magnesium +2, aluminum +3, silicon +4, phosphorus +5. But we see, you know, phosphorus, not all compounds of phosphorus are +5. PCl3 is a very common phosphorus compound. What's the oxidation state of phosphorus in PCl3? PCl3 is a +3 oxidation state here. And so plus 3 means we lose the 3 p electrons, leaving us the s electrons. And so we can ionize these first 3. Well, ionizing the first 3 seem okay, right? 1,000, 2,000, 3,000. Ionizing the s now, that's getting an additional 5,000, additional 6,000. And so phosphorus in the plus 5, which would be something like PCl 5, where we got phosphorus in the plus 5, is going to cost significantly more energy. So you need a good return in order to do that. And the return is going to get there by forming the bonds. And so phosphorus plus 3 ionizes these. Phosphorus plus 5 will ionize the remaining 2. But the question is, why not just stop at phosphorus 1? Well, you know, phosphorus 1, you got that energy, but you don't get much return. And so this is just a balance in cost versus return. And so this is why things stop where they stop, because of what you end up with at the end. But certainly phosphorus plus 6, are you going to see much phosphorus plus 6? No, because look how much energy that, I really doubt you're going to see anything with phosphorus plus 6. Sulfur, you know, like if you look at sulfur SO, you know, that's plus 2. SO2, that's plus 4, right? SO4, 3 minus. Excuse me, not SO4, 3 minus. SO4, 2 minus, that's plus 6. So sulfur, we're going to see variable oxidation states, depending on how many of these electrons we pluck off. But will we ever see sulfur plus 7? No, we aren't going to see sulfur plus 7. And so here we're going to use the ionization energies to tell us, and these are the successive ionization energies. You know, I1 is ionizing the first, I2 is the second. We call this second, third ionization, fourth ionization, fifth ionization, etc., depending on how many electrons there are. Now, ionization energies are going to follow a pattern, a periodic pattern. We can see the periodic pattern right here. We take a look at this, and we see this. Sodium is about 500. As we go across, what's happening to the ionization energy? Ionization energy is increasing as we go across a period. The ionization energy increases as we go across because the ionization energy increases as the size decreases. And so the bigger the atom is, the easier it is to pluck off an electron. The smaller the atom, the harder it is. And so the species with the highest ionization energy should be helium. The species with the lowest ionization energy should be francium or cesium, because francium and cesium are going to be the biggest atoms. But there's a little funny stuff going on here, because this is greater, right? But going from magnesium to aluminum, it doesn't increase. Aluminum is smaller. If aluminum is smaller, it should be harder to ionize, but yet it's easier to ionize. And so when we see an exception like this is an exception, and this is normal. It should increase. This is normal. But here's another exception, because it actually drops down. This is normal. This is normal. And so the size is decreasing as we go across. But there are two exceptions. Here, aluminum is smaller than magnesium, but it's easier to ionize. And here, sulfur is smaller than phosphorus, but it's easier to ionize. And there are reasons for these two exceptions. The first exception is due to what electron we're ionizing. If we look at magnesium, we're ionizing one of the 3s electrons. If we look at aluminum, we have a 3s and a 3p. If we're going to ionize, which one will we ionize first? We're going to ionize the 3p. And so what happens is, it's easier to ionize the 3p. The 3p electrons are less penetrating. And so the reason for this exception is we're ionizing a 3p. Over here, we're ionizing a 3s. 3p are less penetrating, and therefore easier to ionize than a 3s. Now we're ionizing 3p's once we're past that, and so it's just going to go along with the size. And so what's happening between phosphorus and sulfur? When we look at phosphorus, for phosphorus, we have 3s, 3p, 3. And so two common oxidation states for phosphorus are plus 3, we lose those, and plus 5, right? Sulfur, we're ionizing a 3p electron as well. But the difference is, in sulfur, there's a paired 3p. And so in phosphorus, we ionize one of these unpaired p electrons. In sulfur, we ionize a paired. Now, if you have 2 electrons in one orbital, both electrons are negatively charged, so you have electron-electron repulsion due to the negative repulsions. And so what we have in this case is a paired electron is easier to ionize. And so this is paired versus unpaired electron. Unpaired electron will be more difficult. A paired electron is easier to ionize because of the electron-electron repulsions. This is just looking at the first ionization energy here. And so we can graph this. The smallest atom on this chart is going to be helium. Helium's way up here with the ionization energy close to 2,500 kilojoules per mole, very high ionization. Hydrogen's way lower. Hydrogen's ionization energy is only about 1,300. The helium's more than double. And then lithium. Lithium's ionization energy is a lot lower because lithium becomes a bigger atom because there's a whole nother shell. And since lithium is a bigger atom, but as we go from lithium, we'll go from lithium to beryllium. And then there's a drop to boron. And so here's an exception. Well, beryllium, we're ionizing a 2s. Boron, we're ionizing a 2p. So it's easier to ionize a 2p than a 2s. And then we go to carbon, which is here. It's carbon. And then we go to nitrogen, which is here, and oxygen. Nitrogen and oxygen, that's another exception. Nitrogen, we're ionizing an unpaired electron in the 2p. Oxygen, we're ionizing a paired electron in the 2p. And so a paired electron is going to have electron-electron repulsion, so that's why we see this little blip here. And so these 2 exceptions here, even though the size is decreasing, are shown here. And these exceptions are repeated here, here, but the exceptions become less and less significant. You know, as the orbitals get bigger and bigger, electron-electron repulsions aren't going to be that big of a deal. And when you get to very big orbitals, then both aren't very penetrating. You know, the p versus the s. Big orbitals aren't going to be. And so it doesn't become, it becomes less and less pronounced. And then there are other exceptions here. And so this is for the first ionization energy here. And so we just saw one trend. As we go down, for example, lithium, let's take a look at group 1. Lithium's the smallest, cesium's the biggest. So cesium's a big atom, lithium's a small atom. Cesium is going to have a much lower ionization energy. It's going to be a lot easier to ionize than lithium. Lithium's a small one, and it's a lot harder to ionize. And we can see it's a lot harder because this is 500, this is about 400. But that leads to something odd, because if it's easier to ionize cesium, then cesium is going to lose electrons a lot easier than lithium. But what's the most powerful reducer on the chart? Lithium. In fact, lithium is a more powerful reducer than sodium, but sodium, you could lose the electron a lot easier. It's only going to cost you 500 versus 520. And so something doesn't make sense. And it's true, it doesn't make sense because the redox chart ranks it according to what it makes in the end. And so what happens is lithium is harder to ionize. And so it's harder to take the electron off. So lithium isn't as good of a reducer, but it forms a more stable product. Because when we're looking at the product depends on the charge to size ratio. Lithium is a very small ion, and therefore it's going to form a stable product. And so in the end, it's more stable. But initially it isn't. Initially, cesium is the strongest reducer, followed by rubidium. In fact, cesium, you know, if you put lithium in water, it barely reacts. It reacts very slowly. If you put sodium in water, it catches on fire. If you put potassium in water, it explodes. If you put cesium in air, it explodes. And so cesium for sure is the most reactive initially, but it just doesn't yield as much energy in the end. And so all these are much more dangerous than lithium. Although it looks like lithium's the most dangerous, it isn't. And so that's one thing. Okay, when we form cations, we look at ionization energy. When we form anions, we look at electron affinity. And so here, fluorine has a very high electron affinity. It wants an electron to form fluoride. We look at delta H, EA. EA stands for electron affinity, minus 328 kilojoules per mole. So this is highly exothermic. And so this is no problem. This is going to go from less stable to more stable. Here. What's the most powerful oxidizer on the chart? Fluorine. And so it makes sense it has a very high electron affinity. The strange thing is, it doesn't have the highest electron affinity. And for sure, fluorine is the most reactive. Fluorine's the most reactive. It wants the electron the most. It's the most electronegative. But it doesn't have as high of an electron affinity as chlorine. Chlorine has the highest electron affinity. And it's not because of the initial reactivity. Just like lithium. If we're looking at initial reactivity, lithium's not very reactive. Sodium, potassium, rubidium, and cesium are much more reactive. But what we're looking at is the final product. And the same thing with electron affinity. What we aren't looking at is the initial reactivity. When we look at electron affinity, it's a composite of two things. Electron affinity depends on the electronegativity, and fluorine has the highest. And so we look at electronegativity plus one other thing. And the plus one other thing is going to be how well it can accommodate an electron. And so we'll just say accommodation of electron. So fluorine has the strongest pull on the electron. So if we're looking at fluorine, fluorine wants an electron to fill its final 2p orbital. And so this will be a 2p, let's say 2px, 2 electrons there. Whereas chlorine is going to have a much weaker pull. And so when chlorine pulls an electron, but what we see here is if we cram 2 electrons in a small orbital versus 2 electrons in a big orbital, 2 electrons in a big orbital can get away from each other. And so there's less electron-electron repulsion here. And so even though fluorine is a heck of a lot more reactive and a lot more dangerous than chlorine, in the end, chlorine gives us more energy in return because it can accommodate the electron more easily. Okay. Well, we aren't going to worry about that. We know that fluorine is the most dangerous stuff. And that's what we're going to concern. These numbers are just for doing thermodynamic calculations. Everything else behaves as expected. The noble gases, they don't want an electron, so the electron affinities are going to be highly endothermic. These are endothermic as well. If you look at most of the electron affinities, they're all exothermic. These are endothermic because we have a filled 2s. And so the next electron goes into 2p. Well, 2p's is penetrating. And so that's the reason for these. Those you don't have to know as much. So we come up with a statement. Normally in Chem 4, you're taught that you want to form ions that are isoelectronic with noble gases. Why? Because they're more stable. But in reality, the energy doesn't agree. For example, if you went from magnesium to magnesium 2+, this is going to be about 2,200 kilojoules that it's going to cost you. If we go from oxygen to oxygen minus, we get minus 141. That's good. We get some energy in return. But if we go from oxygen minus to oxygen 2 minus, it's plus 744. And so going from oxygen gas to oxygen 2 minus gas is going to cost you about 600 kilojoules. So altogether, forming the ions with the noble gas electron configuration is going to cost a total of 3,000, or close to 3,000, 2,800 kilojoules. 2,800 kilojoules to form the ions. Oxygen's a great oxidizer. Magnesium is a great reducer. And yet, when you look at these numbers, they shouldn't react. And so what's the reason they react? The reason they react is because of ionic bond formation. Ionic bonds, you have +2, -2. They're going to be held together by the bonds. Actually, I should try to be more accurate. +2 is going to be small, -2 is going to be big. And so with cation, anion, we form what's called an ionic lattice. When we form an ionic lattice, we're going to form a lot of bonds. Those bonds are going to stabilize things. And so even though the cost is high, the return is big. Here we get our big return by bond formation. We could get an even bigger return. We could get a bigger return in bond formation if we went higher charge, magnesium 3+ and O3-. This is going to yield much more energy. If we use Coulomb's law, this is 4 times. This would be 9 times the return in energy. And so if we can form a lattice of +3 and -3 ions, it's going to be a lot stronger than a lattice of +2 and -2. But this doesn't happen. Why doesn't this happen? Why this doesn't happen is because it costs too much energy to ionize a core. Well then, you know, if that's the argument, then why don't we stop at +1? We stop at magnesium +1 and we stop. Because here, why did we go to 2-? 2- is going to cost us an additional 744. We should have just stopped at oxygen -1, right? If we stopped at oxygen -1, that's actually exothermic and that's actually good, right? And so this is going to cost us a lot less energy. And so if this costs us a lot less energy, then we should just do this because it's costing us a lot less energy. But what's the problem? The problem is, even though this costs us a lot less energy, the lattice is going to be a lot weaker. Using Coulomb's law is the charge on A times the charge on B. Did I talk about Coulomb's law? The charge on A, +2, charge on B, -2. That's 4, right? This one, the charge on A, +1, charge on B, -1. That's 1. The lattice is 4 times stronger by just costing a bit more energy. And so the reason is nature's going to find this balance where it's going to maximize the benefit for the cost. And so the best cost to benefit ratio is when we stop at the Nobel gas electron configurations. And so, yes, it's going to cost you more to go to +2 and -2, but it's well worth it because the lattice is 4 times stronger. Well, the lattice 4 times, this lattice would be 9 times stronger. Why don't we go here? Well, because the cost of the energy cost is going to be too huge. The cost is 10 times more to ionize a core electron than a valence electron. The core electrons are just roughly 10-fold more difficult. And when we look at successive ionization, you know, the first ionization cost us this much. The second ionization is usually double that. And so double that is okay, but 10-fold of that is too much. Okay. And so that's what's happening. All right, so I'm going to stop here. I'm not finished with 9, but almost finished with 9. We'll finish 9 at the beginning next week. I'm not sure how much 10 we're going to have on this next test. But we're going to start 10. Do you guys remember how to do Lewis structures? No? You're going to be drawing out Lewis structures. So if you don't remember, here's the little outline. Count the total number of valence electrons, not the total number of electrons. It should be valence. You don't want to do core electrons in a Lewis structure. So count the total number of valence electrons, draw a skeleton, place 2 electrons in each bond, identify the terminal atoms, complete the octets of the terminal atoms, subtract the number of electrons used. If there are extra, place them on central atoms. If there aren't enough, we form double bonds. Here, multiple bonds. There's more steps that are needed because sometimes there's conflicts, and we'll look at those. But just start. The first part of experiments 8 and 9 is drawing the Lewis structures for all of them. And so just go ahead and get started trying to refresh your memory about how to draw Lewis structures. And then we'll look at the conflicts that come up. And so we'll use just the remaining minutes to just start writing out the Lewis structures here.